So my name is Bob Jacobsen, and you are at the Math and Physical Science first lecture. I'll give you a little bit of an overview about what we mean by math and physical science in a second. But first, because this is a first lecture, let me go over a little bit of the logistics. You are now in earthquake country. So if there is an earthquake, go to the exits, they're all marked. If it's a fire, go to the exits, they're all marked. If it's a bad lecture, my name is Charles and I'm from the business school. So what we want to do today is a little bit, this is a new thing because this is the first Golden Bear orientation. The first 2/3 or perhaps a little bit more, I'm going to do three things. I'm going to start talking about what it is to learn physics, which is my specialty at Berkeley, mostly at the level of sort of freshman physics. And then I'm going to very quickly transition into why physics is something we actually do at Berkeley and talk to you about how we do that. And then I'm going to go back at the end and very briefly talk a little bit about the rest of the trajectory for a physics student at Berkeley. And I'm going to be followed by my colleague, Professor Antonio Montalban, who will talk about math, which is not physics, and physics is not math. But first, I want to talk a little bit about this idea of math and physical science. Berkeley is so big that you have to divide it in chunks. You have to sort of divide it fractally to get it down to a size that you can deal with. And in this very large College of Letters and Science, we have five divisions, one of which is math and physical science. It's these departments, astrophysics and physics, which are literally next to each other, math and statistics, which are in the same building, and then earth and planetary sciences, which is about 100 meters away. So it's a small complex up in that end of the campus that handles all of this. Of course, the people there have very close connections to things like chemistry, data science, computer science, material science. At the level of research, at the level of teaching, at the level of learning, this is not an isolated little castle. But it is a unit that works together very, very closely. And all of the staff and faculty who work in these areas really work with each other all the time. In fact, you'll see when I talk about my own work that it's actually hard to tell whether I'm a physicist or an astronomer, but I'm a physicist. Trust me, I'm a physicist. Okay, how many of you took AP Physics? Of those who have your hands up, how many of you liked it? Oh, that's depressing, actually. This big black thing on the stage is, so my PowerPoint foo is actually very, very small. I usually work with a blackboard, so when we get to the next picture, don't laugh. So already you know not to follow instructions. That's excellent. This is an inclined plane. Now, one of the problems in the teaching of physics is that people believe that you can teach about inclined planes with things like that. Tiny little text that says, suppose you place a 10-kilogram box on a frictionless 30-degree inclined plane and release your hold, allowing the box to slide to the ground, a horizontal distance of, can't even read that, meters, and a vertical distance of something else, and it's like, ugh. I do this for a living, and my reaction to that is, who the hell cares? It's actually worse than that, because if you're one of the people who has to grade the AP exam, what they give you is this, 2 points, an expression for the sum of the force components parallel to the ramp, which looks like, for indicating that when you do this way, you are fundamentally at risk of this problem, which is hell's library, there's the devil, this poor person looks a lot like me, actually, and he's faced with the library that's story problems, even more story problems galore. The thing you have to remember is that physics is not story problems. Physics is trying to understand and predict what happens in the real world. The science of physics is discovering that you're wrong about what you understand and trying to make that understanding better. So if we actually play with an inclined plane, Galileo did this in 1638. And so to a certain extent, this experiment's been done. But I want to do it anyway with you. Here's a ball. Here's a plane. And I'm going to just tick off seconds. Right? This is not high tech. Actually, Galileo probably did something like this because he didn't have a watch. He didn't even have a clock. So he probably did something like this. I'm going to try and do it without watching. So I'm not saying, oh, wait for the right moment to do the tick. Ready? 1, 2, 3, 4, 5, 6. If I got it right, this time I'm going to watch. It should move about one of these things in the first second, and it should move about 3 more, and it should pretty much hit where the letters are. So 1, 2, I'm a little fast. It is an experimental science. So this is why PowerPoint is so good. Is I'll show you a visualization in just a second, but after the 1, the 2, the 3, the 4, and it hits the end. So really you're seeing something that looks like, back up to the screen, it looks like this. Goes a little bit, goes a little further still, and then it falls on the floor. Sometimes it does that early. If we look at the shots, it looks like that. Now, you got to remember that physics is an experimental science. And when this was done for the first time, I mean, even here, knowing how it's going to turn out, balls fall off, the timing is not perfect. Sometimes the data gets pretty ratty, but you can eventually turn these things into measurements. You can say, I'm going to measure that far, I'm going to measure this far, I'm going to measure this far. Maybe I'll make a table with some data in it because tables are always really, really cool and my handwriting is terrible. And I will infer from this that these are looking like the squares of numbers. This is looking like 2 squared, and this is looking like 3 squared, and this is looking like 4 squared. And if I was very careful to arrange things so that it went 1 spot, 3 spots, 5 spots, instead of some number of centimeters, and Galileo didn't have centimeters, we can get a formula for all of this that looks like that. Now, this is freshman physics. In fact, if you take physics 7 or physics 5, you'll encounter this formula sometime in the first week and a half. And for those of you who took AP physics, it's going to be a memory. Now let me ask you a question. What's that? Acceleration, the letter A. I heard the letter A. That's a nice literalist answer. Something in parentheses, another literalist answer. Actually, in this case, it's 1. The way you get this data to work is by having that be a 1. What that really is something that is very specific to this experiment, because if I tilted it up, it would go much further, and the numbers would be bigger. If I counted for longer ticks, if I went 1, 2, I'm not getting to 3. The numbers would be less longer. So this is all the details of the experiment. They're boiled down into something that we don't know how to predict. With the physics I've taught you here, that's just a magic number that fits to the table after I made it up. I can make the table up, I can do the experiment, and I just put that number in. Whenever a physicist sees something like that, their first reaction is, aha, there must be something that determines that. There must be something that causes that. I want to understand that. There's a difference between the physics of gravity, which comes from a few relations and some simple calculations, and a phone book that consists of every possible masses in the universe and the gravitational force between them. I've discovered that people nowadays don't know what a phone book is. Do you guys know what a phone book is? It's like this thick, and it's got a gazillion entries in it, and you have to look it up, and if you don't know how to spell a person's name, you're just out of luck. You could imagine that the way that we understand gravity is to have the big book of gravity, where you can look up, well, I want to know how much force there is between Jane and Arnold, and I'm going to, A's, 0.07 newtons. But there's no understanding there. Similarly, I want to understand what that is. And going forward only 50 years from Galileo, from where we stand now, that maybe looks like a long time, but at the time it wasn't. You get to Newton. What's Newton's first law? Mutter, 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 acceleration, mutter, 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 mutter. Actually, Newton had many laws before he got to physics. He was the Chancellor of the Exchequer and a member of the British Parliament. So there are a lot of laws with Newton's name on them before you get to physics. But the thing that we call Newton's first law is this one up in the corner. F equals ma. Well, okay. That allows us to figure out some acceleration in terms of the mass, let's say, of this physicist. So that, in my case, that's a very large number. And some force that we don't know yet. So really all we've done is move the problem one to the left. Is that, yeah, one to the left. And also what we tend to do, often making a physicist unhappy, is we approximate them away as a dot. We say, well, she's just gonna be a dot. And then we say, okay, the force that we know best about is gravity. Gravity will generate a certain amount of force per kilogram. Here's that force. What's the physicist about to do? I heard fall. That would not be my first reaction in this situation. I think I would scream, right? Because, yes, she's about to accelerate downward. And those of you who have spent way too long in AP physics will say 9.8 meters per second. Those of us who are experimental physicists will say 10 meters per second, or maybe 32 feet per second, and she's gonna fall. But you have a force of gravity on you, and you're not falling. Nobody's falling, right? Maybe you're falling very slowly, very, very slowly. In fact, let's wait 10 minutes and see how much further down you are. Since the majority of physicists at any given moment are not screaming, we must have missed something with this 32 feet per second. And what did we miss? The floor, yes, that's what the floor. At least for me, it's the floor. For you, it's the seat. Okay, but how does that change the situation? Because this force is still here, and F equals ma, and that, since I know the force and I know the mass, now I know the acceleration, and if I know the acceleration, I put it back in the other formula, blah, 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 blah. I do a word problem, but you have to understand. Well, there are actually two of them, and the thing that we've got to change here is actually get Newton's formula right. It's the sum of all of the forces. I got one and I got two, taking into account their direction has something to do with it. Now, you think you're done at this point. It must be that gravity is pulling her down and the floor somehow is pushing her up. And if the floor is really, really smart and can do its calculations to many decimal places, those two will be exactly equal, and she won't go anywhere. So now, what's the obvious question? How does it know? Floors are not very high tech. They don't have processors in them. How does it know? How does the floor know to put just exactly the right amount of newtons or pounds up to keep me from falling through it? And does it have a sense of humor? Will it go out to lunch and stop doing it at some point? But in your case, you're sitting in a chair. There is a gravitational force and there's a butt force, and the combination of them is exactly equal to 0. And how does, is there high-tech communications between the seat and between you? How does it know? If it gets it even a little bit wrong, you won't fall as fast as if you're in free fall, but you'll fall or you'll go up depending on if it's too little or too much. How does it know? This is actually a very interesting question. It's actually a fascinating question. If you follow this as far as it goes, which those of you who are studying physics will follow it a long way, you'll learn a lot. But here's an example. So it's not done by sitting something on it. We're actually using this spring to hold up this mass. Can you guys, I think most of you in the front might have a little trouble seeing it, but can you see the thing I'm pointing at? What color is it? Okay, I can't see colors, so that's good. You pass. And this is this, and I'm going to use a word now, equilibrium condition that we had before. It's being held up. So the force of the spring and the force of the gravity must be exactly equal. What would happen if I just reduced the amount of force from the spring? I'm going to do that by sort of using my hand to pull it down a little bit. What do you think the block would do? Oscillate is a big word. How about fall? And then it's trying to decide where its new equilibrium is. In fact, if it's ever the case that maybe I move it up a little so the spring isn't pulling up on it enough and I let it go, it'll fall down until the spring generates more force and pulls it up. And then it'll come up until the spring generates not enough force and it starts to fall back down. I want you all to lift yourselves about an inch out of your seats and very slowly lower yourself down into your seat and decide how the seat knows how much to push on you. Sometimes it's the seat that moves, sometimes it's the gluteus maximus that moves, but when you're up, there's not a lot of force, and as you slowly go down, there's more and more force until eventually you're matched and you stop. And if you push yourself down in the seat extra, you'll pop up a little bit, right? If you overshoot, you'll pop up a little bit. The idea of an equilibrium, the idea of a bunch of forces that change with small changes that result in things trying to push back toward a central point that's stable, describes a tremendous amount of physics. It's a really important idea. And you don't want to miss it by just doing a calculation of so many newtons up and so many newtons down. One of the things that's going to happen to you as you take all of your lower division physical science courses, whether it be math or Earth and planetary sciences or astronomy or physics or statistics, is that we're going to be forcing you to think beyond the formula. Sometimes that can be hard. It's also the case that when you think about the details of this situation, it's more than just writing down that it's a vector sum and playing with a lot of vectors. It's true that if we think about this ball, there's this force of gravity, and there's somehow a force that's coming from the plane that is this thing. We call it the normal force because we don't want to embarrass it. And it goes up this way, and that they don't quite go in the same direction, so they don't quite cancel. So there's a little tiny bit that's out here. But if you're not careful, if you just memorize the formulas for how to figure out what the normal force is, you miss a lot of very interesting physics. You miss a lot of stuff that's actually happening here in this interaction of the ball and the block, in this interaction of rolling as it goes down that matters. But still, this is enough to be able to handle this case that I wanted to come back to from before of when I changed the angle of the plane. We'd sort of pick it up and tilt it. It's heavy enough that I'm not going to do that because that changes this. Gravity hasn't changed, but this normal force has changed in magical ways that we would have to think about, and therefore the sum changes, and therefore it goes down these ticks much faster because that's a higher acceleration. So believe it or not, that's enough to do a lot of physics. It's actually an inefficient way to do a lot of physics, because if you think just in terms of forces and motions, you may have to handle an awful lot of detail. So this is a pendulum. I love this pendulum. You can think of it as a pendulum because, let's see, that's going that way, let's go this way. So what are the forces on this at the moment? Well, there's something that's going that way, right? Because you can pull on a string, but you can't push on a string. And gravity is still down, and trust me, this is a bowling ball. It's got a fair amount of gravity on it. And my hand is on it, too, right? Because there's a downish force, and there's a that-way-ish force, and somebody's got to be balancing it with a that-way-ish force if it's not going anywhere. What happens when I let it go? Actually, I wipe out my laptop is what happens if I let it go. So I'll stand here, and maybe it'll be okay. I don't like that laptop. The motion is actually much more complicated than the plane because this angle is changing all the time. Now we got the steep plane, and over here it'll be the less steep plane. It's also moving faster and slower as it goes across. Its motion is very complicated. So now this is a test of the teacher's ability to do a tremendous amount of algebra and a little bit of calculus in real time. Yes, I am safe here. So how did I know? It's actually well clear of the laptop. That's unfortunate. But it is precessing a little bit. It's moving a little bit forward. So there are three things going on here. One is Newton's laws, a little bit of kinematics, 1/2 AT squared, will go a long, long way. But sometimes it's better to think about things with bigger terms. And in this case, thinking about this with energy works a lot better. By taking it and pulling it all the way over here, you can think about it in terms of I had to push on it and do a lot of energy injection or work, or that I lifted it up this much and put in energy or work. Now I can think about how that works very easily. It doesn't have enough energy to lift itself up a little bit higher and slap me in the nose, he says confidently. There's actually another piece going on that you might not be able to see. Where's the top end of the string? Those of you in front have an advantage on this one. Where's the top end of the string attached? There's a light bar up there in the catwalk. And do you notice it's starting to move? It's starting to swing too. This is a phenomenon known as resonance. If you hit something, see, I knew I was going to do that at some point, and we're going to save the laptop. If you hit something even a little bit at just the right time, over and over again, the classic example is pushing your little brother on a swing, where you're looking very innocent. Everybody thinks that you're being nice, but you're just pushing each time, and he's swinging higher and higher, and then he starts screaming. And you're saying to your parents, no, I was just pushing. It's nice, it's cool. And your brother's going, he's trying to kill me. The same is true here. Both the string and the light bar have natural frequencies at which they want to swing. And although I'm only pushing on the ball, there's a coupling through that rope that also pushes on the bar at the top. And the exact timing of that can be very critical as to how it moves. A very small thing, perhaps a negligible thing, but something that you need to understand. Okay. Are we tired of freshman physics? A little bit? I am. I want to talk about something which I put on the slide. This is my favorite slide of the talk. This is dark matter. You think I'm kidding? Actually, let me ask a question first. What's that a picture of? So somebody actually knows. Somebody's seen this picture before and called it the Hubble Deep Field. It's actually part of the Hubble Deep Field. But what are the glowing things? Well, so a few of them are stars. There are less than 10 stars up here. That's a star. That's not, even though it looks just like it. And there's one down here. That's a star. Oops, right there. That's a star. But the rest of them are galaxies. Now, first going to be the first question. That's the easy one. Then there's going to be the second question that'll stop you in your tracks. What's a galaxy? It's a great big station wagon that Ford made from 1963 to 1975. No, seriously, what's a galaxy? Bunch of stars, island universe, swirling bunch of stars. Okay, how do you know? Right? The fundamental question of physics is how do you know? Because don't forget, in science, most of what you know either has been very carefully confirmed, or we have a technical term for stuff that's not confirmed. It's called usually wrong. And let me remind you, that big shiny thing in the sky that you only see sometimes in Northern California, right, and which will go away on Monday for a little while, what's that called? Where does all that energy come from? Thermal fusion, thermonuclear fusion. How do you know? You read it somewhere. That doesn't count. Just because you read it doesn't mean it's true. How many of you have heard of Darwin? What's Darwin famous for? Evolution. The book he wrote is called The Origin of Species. How many of you read The Origin of Species? Even though you're all future physicists, I recommend you read it. In the very first version of it, toward the end, he was mostly talking about the origin of species, where variation comes from. And the idea of survival of the fittest was in there, but that it was about variation. And in the I think it's very close to the end, within a few pages of the end, he says that these processes, I'm not quoting exactly, but it's pretty close, these processes could account for all of the variation of life on Earth, which was a heretical thing to say at that point. But that process is slow, and it might take a long time, perhaps even tens or hundreds of millions of years. And he got called out by a physicist, Lord Rutherford, who wrote to him and said, well, then you must be wrong, because we all know that the Earth can't be any more than about 5 million years old. And the reason for that is that Rutherford had done a calculation of how much salt there is in the ocean, and salt goes into the ocean but doesn't come out. And figured out, even if you start with fresh water and you let it accumulate as rivers bring salt into the ocean, it take you roughly 5 million years to get to where we are now. So what did Darwin do, like a good biologist? Did he fight? No, he changed the book. And he said, could account for all the variation, except that it might take a really long time. Period, move on to the next chapter. Brilliant strategy for a biologist, because of course the physicist was wrong, but there's no way you were going to convince him of that. We've had 5 different models before fusion for how the sun shines. And they were all believed, they were all taught, they all appeared in textbooks, and they were all wrong. And it was only when fusion arrived, a guy by the name of Hans Bethe came up with that theory in the 30s, which is almost within living memory. You may have relatives who were alive in the 1930s. And there was a test done by a guy by the name of Ray Davies, who put a giant tank of cleaning fluid, trichloroethane, in an underground gold mine in Homestake, South Dakota, and detected a few atoms being converted by neutrinos that come from the sun. And finally, we had evidence that our theory for why the sun burned was right, at least within a factor of 3, and I'll come back to that. So part of what we do at Berkeley, part of what we do in science, is try to prove whether things are right. Here's one of those things. If you're trying to figure out what those blobs in your telescope photos are, what would you do? Unfortunately, 100 years ago, we did not have the technology to put a graduate student in a rocket and send them to a galaxy and say, right back when you get there. We don't have that now either, but we can dream about it now. This is the observatory that was built on a mountain, Mount Wilson, not very far. It's Lick Observatory. It's not very far from here. It's in the mountains right above San Jose. On a clear day, if you can get a good southern view, you can see it from here. That dome is now bright white. And it was built to understand these kinds of questions. The thing they put inside the dome was a telescope. I love this picture of telescope. Why do I love this picture of telescope? These are guys. They're inside. They're wearing hats. This dome was so big that it had weather in it. Clouds would form and it would rain inside the dome. This was the telescope. Here's somebody looking through the telescope. Can you imagine the job description? Look through a very, very large telescope. It's not actually a photograph, but it really did look a lot like that. And the very first, they had some other stuff they wanted to look at first. They really built it to look at planets and some nearby objects. But when they first started getting photographs at this and other telescopes, they looked like that. And the light is not perfect here. It's actually pretty good. The projector is really good. The image is garbage. Because the technology was 130 years ago. This picture, I want to make sure I get the date right, because that matters, was taken in 1898. This one is from 1914. You're beginning to see swirls, but you're not beginning to see stars. And if your theory is that this is stars, big honking things, like the thing that keeps us lit, you've got to believe this is huge and very far away. If you think it's glowing gas, it can be much smaller, much closer, and in some sense more believable. So how do you know? Well, one thing you can do, once you start finding ones like this is a 1926 picture, and it's one of the ones that appeared, that was used in the data for the first time this was done in the 30s. is that if that's spinning, one side or the other, you don't know which, is coming toward you. Right? Might be spinning this way, might be spinning that way, you don't care. One side is coming toward you, one side's going away. Even if the whole thing's flying away, one's coming toward you a little bit more or a little bit less. And once you have spectrographs that can take these very dim images on the sky and measure, using the Doppler effect, the relative velocity of the left side versus the right side, you can start to determine whether it's really spinning. And if you want to do that precisely, what you actually do is you sort of measure how fast it's spinning in little slices. Because you understand gravity. We were drawing arrows with gravity. You understand circular motion and curved motion. And you can work out how fast these things should be moving if there's that big central bulge of gravity that's pulling them in and everything is stars orbiting around that. You would expect that it's something like this curve. Close in, everything has to orbit pretty quickly because it's very close to a lot of mass. Further out, it's orbiting slowly because really there's not a lot of mass out here. It's mostly in that bulge. And you might have small corrections for how much mass you can imagine is in stars or in gas, but this basic thing is true. The good news is they are spinning because you see left versus right. The good news is you can actually measure these velocities and convince yourself that it's a very far away accumulation of very bright things and it must be stars, but the curve looks like this. This often happens when you confirm something that you didn't know. It turns out that most of what you knew was right, but you screwed up the details. That happens a lot. When Ray Davies confirmed how the sun burns, he saw that only a third as many events in his detectors as he expected from the sun. And people thought, well, maybe the sun isn't burning exactly the way we expect, or maybe something's absorbing these. It turned out that the neutrinos that he was seeing have different properties from what we expected, and so we learned something new by verifying something else. And here, well, there are three things that this could be. It's very important for an experimental physicist. Astronomers never make mistakes, but experimental physicists do all the time. This could be a mistake. So you want to repeat it. You want to try it with other galaxies. You want to try it with other spectrographs. You want to try a whole bunch of stuff and make sure you didn't screw up. It could be that our theory of gravity is just wrong. It could be that gravity doesn't get weaker as fast as we think as you go across huge distances. Distances larger than we've done any experiments on. Distances larger from here to Pluto. There's something just a little bit wrong in our formula. Or it could be, and this is just like crazy, that the vast majority of stuff in the universe isn't made of protons and electrons. It's something entirely different, which has weird properties, and nobody knows what it is, and we'll just sort of throw it into the theory because we're desperate. Nobody's going to believe this third choice anyway. And incidentally, we need a name for it, so we can't see it, so we'll call it dark, and it has gravity, so we'll call it matter. It's called dark matter. We'll stick it in a drawer, and we'll hope it never comes back out. Well, the problem is that as your instrumentation gets better, you can start making more and more things. This is not the picture that was used for this. This is the Hubble picture because I think it's pretty. But there were pictures of large fields of galaxies where you could measure the motion of the galaxies. You could track them. You can't really see their side-to-side motion unless you're willing to wait a billion years, and it's hard to get funding to do that. But you can measure their fore and aft motion. A guy by the name of Zwicky started this, and others continued it, and it turns out that there's a lot more gravity going on in this picture than you can explain by just what you see. But it could be the theory's wrong. Vera Rubin and her colleagues spent 20 years making these measurements over and over again. This is a paper, one of many papers on 21 galaxies made with 2 spectrographs. There are no error bars here because astronomers don't believe that they ever make an error. Physicists put error bars on their plots. It's a sore point. But it clearly has that we're not going up and falling back down. We're going up and staying flat behavior. And we begin to believe that this stuff is real. We really do begin to believe that there's something to this effect. But as to the possibility of the dark matter itself, here's exactly what we know. Still nothing. The point at which dark matter became a real possibility, not the crazy third choice you put in the drawer because you're just covering your bases, was when this observation was made. Other scientists will give you different stories, but this is my story, and I'm sticking to it. This is called the Bullet Galaxy, which is a misnomer because it's actually two galaxies. It's a galaxy that was going this way and a galaxy that was going this way, and they simply failed to yield at the stop sign, and they ran into each other. Now, this is a rare event. Galaxies basically don't do this, but in a big enough universe, rare events happen. And an interesting thing happened. This is actually in the background. Ignore that. These are all in the background. This stuff is the hot gas and stars of the galaxies. And they sort of went through each other. A galaxy is mostly open space. The stars, like the sun, does not fill our solar system. And our solar system does not fill the distance to the nearest star. But if you run two galaxies through each other, some of the stars are going to come close enough to each other that they're not going to go straight by, they're going to deflect. They're going to feel a very strong gravitational force if they go close enough, and they'll bend out. And this has the effect of basically converting some of the linear, very idealized motion into heat, into spreading, into tearing apart. And it slows down those stars because their speed is now going this way instead of going that way. So the galaxies basically got sort of shredded. But all of the hot gas doesn't really do that. Gas molecules don't have big gravitational effects on each other. They're just little molecules. And so they go right through and they continue. And the gas is hot. What's hot stuff? When you say a gas is hot, what is you really talking about? The molecules are moving really, really fast. Well, the hot gas in a galaxy is held there by the gravity of the galaxy. It's held from escaping because it's attracted to all those stars. If I stop the stars and the gas keeps going, it's like I've let it out of a bottle and it can expand. But this gas didn't. This gas continued, and over billions of years, well, it's more like 900 million, but I'm not certainly exactly that number, it didn't expand very much at all. What seems to have happened here, and they've now made some measurements using gravitational lensing to confirm it, is that whatever the most of the mass is, whatever the stuff that's explaining how heavy that galaxy is and how it won't gravitate like normal, but it looks like it's got heaviness in it, kept going. And it's very hard to come up with a theory of gravity that explains that unless you've actually got a physical thing there, this thing that we call dark matter that's going through it. So now you got a mystery that you have to confront. You can't just say, oh, go forth and make a theory. You have to actually confront it. The best theory we can come up with is that the universe is full of stuff that I don't believe exists, and this cold dark matter and the atoms that you and I are made of. And as an experimental physicist, my colleagues and I want to know what this stuff is here at Berkeley. The first kinds of experiments that were not done here at Berkeley. They were done by flying satellites and saying, well, if dark matter exists, maybe sometimes it runs into each other, and in the process of running into each other, maybe it gives off X-rays. The argument is very weak. The argument is very tenuous. It's hard to believe this would even actually work, but sometimes you do the experiment you can. And the problem with experiments that are looking for something in the sky is that you see something. This is energy of X-rays. This is how many you see, and they see lots of them. But there are lots of things that can make X-rays. Stars bump into each other. There's gas flying around. There's all sorts of stuff. You have to predict how much you're going to see, and then if you see more, maybe that's important. The colors, incidentally, are very interesting. This was flown by Stanford. So what they did was for the routine stuff that everybody expects, they used blue and gold. And for the excess that was supposed to be really important, they used red. Luckily, this experiment was wrong. Their detector was not well calibrated, and it turns out they didn't actually discover anything. But people are still doing this. I love this. As you wander around campus, you'll find the Free Speech Cafe. And outside the Free Speech Cafe, there are newspapers from all over the world. They're changed every day. And on December 17th, this was the front page of China Daily. China launched its first dark matter satellite. Pictures of the launch, pictures of the satellite. It's a big deal. It's above the fold on the first page of the newspaper. Look at the headline down here. This is the return of the Star Wars movie. It got second billing to dark matter. I liked that a lot. The movie wasn't that good either. In the lab, what we want to do is we want to hope that these things are particles, and we want to see them somehow bounce off matter. We want to see them, the technical term is interact. And it's hard to do because we already know that this stuff doesn't interact very much. That's why it's called dark matter. But there is some possibility. This is a complicated slide that's here mostly because the union requires that I say that this is a complicated thing. But fundamentally, it's actually pretty simple. What we have is a gigantic tank of liquid xenon. Liquid xenon is a heavy element. Those of you who took chemistry, I never took chemistry. Chemistry, what are the noble gases? It's like helium, unobtainium, krypton, supermanium, xenon, right? Xenon is really heavy, which means that its nuclei are really big. It's noble gas, which means that we can use chemistry to get all the impurities out of it. We can make it incredibly pure, because everything other than other noble gases can be purified out of it. And since it's the heaviest one, it's the one that stays as a liquid. So we can get all the other stuff. Krypton is radioactive, so that's bad. What we actually have is, as this is sitting here, if something hits this, it'll emit a little flash of light. Actually, let me go back one and see if I can get it to do it again. There we go. Hopefully it's doing it. As something comes in, it'll hit an atom of xenon in the center of this and emit a little flash of light and some electrons. And then those electrons will drift up here because we're putting a huge voltage on this. And eventually they'll make it up here, they'll make another flash of light. And we can tell that something happened inside this tank, which is the cleanest and most boring tank in the universe, because there's nothing but krypton in it. Excuse me, nothing but xenon in it. It looks something like this. Lots of copper, big tank. A graduate student by the name of Mia Eam. Everybody's name was upside down on their Tyvek suits for reasons that are lost in history. But here's the actual device. This is sort of hard hat science. This is not, oh, I just build a tank, and I draw it, and by the end of the day, we're done. This involves huge amounts of tubing and moving things around with 5-ton cranes, and everybody but this guy is wearing a hard hat, and he's gonna get in trouble. Ask me how I know. A lot of plumbing, a lot of tags that say, Bob has signed this thing off. If you open it, he will be angry. That's what that tag actually says. Networking for the computers to control it all. The net bottom line is this tank is living inside of a great big water shield. That's all water. This is a person for scale. Inside something. Can you see the person? This is the room that was built to put the detector in. These white things on the walls are bolts that go 10 feet back into the wall, because this is 4,850 feet below a mountain in South Dakota. And if you try to open a volume, an empty space inside a mountain, what does the mountain try to do? And this is considered bad. Right? If your experiment is reduced from being almost 4.5 meters high to being 3 millimeters high, this is considered bad. So there's a lot of what's called rock bolting that holds it in place. The cavern, it turns out, is where Ray Davies did his work to show that the sun burns by thermonuclear fusion. This is him, and this is his experiment, and they're the rock bolts. We just had to make it a little bit bigger. It's a very industrial place. The physicists get the nice, clean, white hard hats, and the miners get the other ones. Remember this wall, we'll come back to it. And it's in South Dakota because that's where the Berkeley gold mine is. How many of you have been to Hearst Mining? Hearst Circle, you know where that is? As you explore, you'll learn more. Who was William Randolph Hearst? Those of you who are California residents probably know the name. What was he famous for? He started a war. He was a newspaper publisher. Where did his money come from? He built San Simeon Castle. Where did his money come from? His money came from his father, who owned a gold mine. Biggest gold mine in the world at the time. It's right next door. If you go down this valley to just sort of right there is Deadwood, which is a real place. It turns out that the history of the West is full of mines, silver mines and gold mines, that have towns next to them where people are in the business of using liquor and other things to take money away from miners. It's very effective economics. So we got this detector built, and we run it for a little while, and then we get headlines from this one. Lux, that's the name of the detector, dark matter finds no WIMPs, so why are scientists happy? This is from the LA Times, front page of the LA Times. We didn't find anything. Spent years, millions of dollars building this thing. Entire graduate student careers spent underground. We didn't find anything. Why is that good? It means all of the theories about what was happening are too naive. It means that we were wrong. And physicists secretly love it when we're wrong, because it means there's something we don't understand. It means there's something we can study and learn from and do better. This is a little bit dense, but we don't know the mass of the particles that make this stuff up. We don't have a theory for that, so we have to maintain a lot of possibilities. And we don't know how likely they are to interact as they go through, so we have to maintain a lot of possibilities. But basically, we build a detector that can see everything here. So anything up here, if this is the spot that corresponded to the mass, that's about a proton mass. That over here is about a proton mass. That's about a TeV. And that coupling, we would have seen it. We would have seen it. We would have seen it. Down here, we can't see it yet. All this colored stuff, most of which is ruled out, are theories that somebody wrote down to explain this. I expect that there'll be a particle of such mass with such properties. Ooh, that's not there. I expect that there'll be one of, nope, that one, not that one either. There are a few that are surviving, 3, but we're gonna get them with the next experiment. And this is one of my favorite cartoons. I'll read it to you. So the grad student and the scientist. Excuse me, sir, but why are we building a death ray again? Why? To take over the world, of course. But why? Are we testing some sort of mad hypothesis? Well, I mean, I was just describing mad hypotheses. No. Perhaps making some mad observations? Are we at least going to leave some of the world as a mad control group? It really is a sad truth that most mad scientists are actually mad engineers. They're just building things because they can. It's the scientists who are trying to figure things out. So the only paper you could publish on taking over the world is titled something like, "A Measurement of the Effectiveness of the Following Technique for Taking Over the World." One of the things I want to point out is that this is not something that's done by professional mad scientists. This is done by people like you. These are some pictures of a piece of instrumentation. This is about this big inside of its case. It looks a little bit like a pipe bomb, and there's a story about that, but it's a very high precision amplifier that was built by an undergraduate. Her name's Adeline. It looks a little bit like a meatloaf, and she had it packed up in a cooler. It has to be kept cool, and she was taking it on an airplane, and they insisted on looking at it, of course. And then they discovered that it looks a lot like a pipe bomb. And she was saying, well, I built this. And that's the point at which it really started to go poorly. But she was cool, and she got it there. And the people in South Dakota are actually very reasonable. I'm not going to explain this in detail, but this is the result of the device that she built being put inside the detector to help prove that if there was something happening in the detector, that we would see it. Right? If you don't see anything, it could be because you proved that it's not there. It also could be because you've screwed up and your detector was not plugged into the wall that day, or something like that. It's surprising how much attention these experiments, far underground experiments that are not finding the things that people write articles in the New York Times and the LA Times about, that my proof for how much attention they're getting is this slide. Anybody recognize him? This is great. This is a physics audience who doesn't recognize him. Thank you. That makes me feel so much better. This is Mark Zuckerberg. There we go. And he had, there it is, it says here, he had a Facebook Live from the mind. Remember I told you to remember the stuff on the wall? Well, that's the spot. It was taken from the same place as that other picture. He appeared, 6,643 people were sharing, I don't know what that means, and almost 1 million were viewing him going down in the mine and talking about the science, most of which he actually got right. He did a really good job. The interesting picture about this is, you remember the other picture, everybody's wearing these vests with the straps and the reflective stuff and stuff like that. He didn't have to wear the rescue stuff. So if anything had gone wrong in the mine, all the scientists would have gotten out and he wouldn't have. And that was okay with him, because this is the way he apparently always looks. So where have we done? Where have we covered here? We've talked a little bit about our approach to teaching lower division courses. The idea of asking questions, of building things up of teaching you not just the formulas, but how to figure out how a situation works. We're not so much practicing your ability to make answers, we're practicing your ability to tell whether you're getting the right questions. And we do that starting with the very first part. In part, that's because we are about the creation of new knowledge. And I talked to you about one of 3 dozen, maybe 4 dozen projects that people from Berkeley Physics are involved in, which is the dark matter work that's done by Dan McKinsey and others, besides myself. I'm a tiny part of this whole effort. And the part that's missing now, and I've just got one slide on it, is to talk a little bit about the courses that go into this. We've already talked about the idea that there are freshman courses, but the thing that I want to get across to you is there aren't all that many. If you're studying physics or other topics like that, you're typically taking 2 courses a semester, one of math and one of physics, something like that, for 2 years. This is not the only thing you're doing here. You're going to work really hard in those courses, but you have time to do other stuff too. And even, this is straight off the physics webpage, even if you're a transfer student or a junior or senior native student who's been here, you're still typically taking only 2 physics courses a semester. There is time to get involved in research. There is time to sing with a singing group or to learn French or to learn about the world in other ways, to be involved in internships. This will occupy you. This will keep you very busy learning physics. But there is room for other things too, including actually being a physicist, actually working in a research group. So hopefully that's given you a little bit of a flavor of the overall, what did I forget? I need a noun there. What do my notes say? Oh, the overall approach of Berkeley physics to teaching students. And I'm going to actually take my leave now with that, leaving the pendulum hanging there, and introduce my colleague who will give you a little bit of a picture about sort of the other end of the math and physical science trajectory, spectrum, I really should read my notes more, which is mathematics. A very different thing, but still part of this core of math and physical science. So with that, over to my colleague.
All right, can you guys hear me? How are you guys doing? Okay, so I'm gonna give a much shorter talk. I'm not gonna talk about mathematics itself. Just I was asked to talk about the math department and how you guys interact with the math department. But everything, I mean, the math department is the one I know. But what I'm gonna say applies to physics, statistics, and all the other departments in the math and physics division. So I'll talk from the side of math department, but it applies to everything. All right, so I'm a math professor. I've been a professor for a long time, 10 years. And I'm from South America originally, came some time ago. I studied there in a public university, and now I work here in a best public university in the world. Yeah, and you guys are starting at the best public university in the world. So sky is the limit for you guys. Okay, so what do we do in the math department? So, well, the math department has the professors. That's you're gonna interact with us a lot, and we do mainly 3 things. Well, like research and teaching and service. I'm not gonna bore you with that. So research, you hear a lot about what kind of research we do. I mean, it's all different kind of research: mathematics, physics. All the professors here are doing research in something, and we like. Everybody is kind of top at whatever they are doing. So Berkeley has some of the top researchers, and everybody is super good at what they are doing. And all these researchers, when they are not researching, they are teaching you stuff. They are teaching you stuff, not stuff that they learned in a book 20 years ago when they study and now they repeat it. They are teaching you stuff we are doing every day. So you're learning from people that are teaching you what we're doing every day. So real stuff. So what do we teach? At least in math, and it's the same in the other one. So we teach all kind of classes. So like I'm gonna teach an undergrad class this semester. I taught a small class, advanced graduate student class last semester with 8 students. The previous semester had 500 students, like a freshman from all over science. So we all do a bit of everything. So you get to interact with pretty much all the old professors, the new professors. We are all doing advanced classes, undergrad classes. You get to see us all in the classes. And the teaching that's the part that will interact the most. You've been taking classes all the time, working pretty hard. But there are more to that, more to the department to that. And you should take advantage of the other things that we have in these departments. So, for example, what else do we do in the math department? So what else could you do? So there are these directed ready programs. You know what those are? DRPs? Well, you have time to figure it out. There are many things you have time to figure out, and you should. So for example, that one is you can pair with a grad student to learn something, to read a paper, to read a book. That's very common in the math department. People do it quite a bit. But I'm sure there are other things in other departments. You could, when you're more advanced, when you're like a senior, you could do a reading course with a professor. Sometimes you go ask a professor, can we do a reading course? And that means you and your friend and the professor just reading a book. You learn a lot from that because you're interacting with somebody who's an expert on the area telling you stuff. If you can get into a research project, that's awesome. Those are super cool. Maybe hard to get, but they are there. Undergraduates and professors are working together in research projects all the time. So this is also, I mean, when you get further ahead in your studies. But it's not just the classes. What I want to say is that it's not just the classes that the way we interact with professors and with students. What else? Well, there are also all kinds of associations. In the math departments, the undergrads have this MUSA, is a Math Undergrad Student Association. They have a lot of activities. If you guys look it up, I'm sure there are others in our departments. I run a program called Berkeley Connect, which I recommend you guys sign up at some point, maybe not this semester, maybe whenever you want, maybe some semester along your time here, which is a program where, like I run Berkeley Connect Math. There are a Berkeley Connect for other areas. And essentially, we talk all math except for math. We don't do math, but we talk about everything that has to do with math. So about your careers doing a math major or doing a computer science major, what do you do with it? How do you study math? What happens after you study math some years later? So it's a very interesting program that kind of shows you parts of the student academic part that you don't get to see if you're just going to classes like every day. It's very easy to get into that routine of class, study, sleep, class, study, sleep. So it's easy. It's good to find other things to do. So it's interesting. So we run this panel, and Musa runs the same panel once a semester with alumni that were here, like where you are, I don't know, 5, 10, 15 years ago. And now they are out in the world doing all kinds of things. So people that come and do like a math major or even a physics major or statistics, they end up doing all kinds of things. Some end up doing grad school and maybe research, but that's not the majority. And some go to Silicon Valley, and some go to finance, and some go to being actuarials, some biotechs, and some teachers. There is like all kinds of things people end up doing from here. It's super interesting to see people telling you their stories 10 years later. So if you guys are going to end up doing all these kind of things, what is that you learn? What is that we want you to learn? What is that we prepare you for when you do the math major, say, or the physics major? And one of the most important things is that Bob said, or maybe I'll say with other words, is you learn to learn. But not to learn in the sense you learn to read the book, do the test, which that's the way that you have to do that, by the way. But you learn to take a topic, read it, analyze it, understand it, and then being able to solve problems about it. That's a super important skill. And for most of the people that finish their undergrad here and then they hire in industry later, that's the skill they're looking for. Somebody that can learn and something new and apply it. And that's a super good skill. So when we have these panels, a very common question is like, how much of the math that you learn you use? And they will say, yeah, we use some. Definitely we use some of the math you learn. The background is super good, because having a good background, that allows you to learn. But some we don't use anymore. But still, the skills that we learn in those classes that we didn't use anymore, they are useful for life. So that's a very important goal. And like the way Bob said it is also very good. Like instead of just learning the thing, we want you to ask to learn how to ask the right question instead of how to answer the questions. That's how you learn. Okay, so right. So the math department, we have all kind of things. You should all kind of classes. At some point, you have to figure out how to navigate those. There are and the whole university has so many classes. You have your undergrad advisors will help you choose, but there is definitely a lot to choose from. That's gonna be I mean, I'm even envious of you guys that you get to take all these classes, have time to take all these classes. But I want to say one last thing. So Berkeley, okay, so it's a pretty amazing place in the sense that we give you these tools for you to succeed later in life, and these are pretty good tools we give you here. I guess so. What is one of the main tools you get? So what is the one thing that separates the people that are, or the students, even the students that are very successful from the ones that aren't? Okay, so the first thing you would say is hard work. Definitely hard work. You don't have to work quite hard. That's definitely one thing. But another thing is curiosity. Curiosity is something that that helps you learn, essentially. So when you're in, I don't know if you already noticed, maybe you're at that point when you haven't noticed yet, but you will soon. And when you're a teenager, the cool attitude to have is to be like, I don't care, I don't care. When you're in Berkeley, the cool attitude to have is, what, really? Oh, tell me more, I want to learn. And you will see, like, the cool people here, students, the seniors here, have that attitude, like, oh, I want to know, yes, I want to hear more. And that's the attitude that will, like, navigate you through the whole time here. Because you're going to take some classes, well, first, it's going to allow you to choose classes that are absolutely awesome. And second, when you're in a class that is not that awesome, it's actually, most of the classes are super interesting, even if at the beginning they don't look like it. And once you notice that, then you're going to have the drive to learn. You're going to be like, okay, I want to learn this. I want to be good at this. And when you're doing that, it's still hard work, but it doesn't feel like hard work anymore. For me, it was quite a bit of hard work to get here, but it didn't feel like hard work because I wanted to learn all the time. So Berkeley is a great place to cultivate that, because we have people like Bob. He's super interested in what he's doing, and you can find all these people that are really interested in doing super interesting things. And you can find very interesting things to do, and people who have this drive. So it's a really good thing to cultivate this curiosity. And Berkeley is a great place for that. That's all I wanted to say. So that's all for the day. That's all for today. So welcome to Berkeley, everybody, and good luck.